Welcome to This Explainer. Today, we're diving straight into a real masterclass on the physics and mathematics of fluid properties. If you've been wanting to truly master how fluids behave under pressure or figure out what's happening at the microscopic level, you are in exactly the right place. We're going to break down the heavy mechanics behind two absolutely vital fluid properties: compressibility and surface tension. By the end of our time together, you won't just understand the theory, you'll know the exact mathematical equations that govern all this fascinating stuff.
Here's our agenda for today's session. We'll start with 1, 2 essential fluid properties. Then 2, compressibility and bulk modulus. Next up, 3, the science of surface tension, followed by 4, calculating pressure and forces. Then we'll look at 5, real-world engineering applications, and finish up with 6, summary and observations.
All right, Section 1, 2 essential fluid properties, exploring fundamental fluid behaviors.
So picture this. I'm standing right in front of you, and I'm holding two perfectly sealed syringes. One is filled entirely with air, and the other is filled entirely with water. Now here's my question for you. What happens when you press the piston of the air syringe versus pressing the water syringe? Just think about it for a second. If you press the air syringe, the piston moves inward, right? The air just kind of yields to the pressure. But if you try to press the water syringe, that piston barely budges at all.
It all comes down to this really distinct baseline rule of physics. Gases are highly compressible. That means their volume shrinks and changes pretty drastically when you apply external pressure. Liquids, on the flip side, heavily resisted. They are almost entirely incompressible, meaning their volume changes very, very little under pressure. This one fundamental distinction, it's basically the bedrock of all fluid mechanics.
Moving right along to Section 2, compressibility and bulk modulus, understanding the stiffness of fluids.
Okay, so how do we actually measure this fluid stiffness? Well, we use a property called the bulk modulus of elasticity, which we represent with the letter K. Bulk modulus is defined as the ratio of compressive stress, which is just a fancy way of saying the increase in pressure applied to the fluid, to the volumetric strain, which is the relative decrease in the fluid's overall volume. Basically, it tells us precisely how much pressure you need to force a fluid to shrink. Let's unpack the math here together. K equals negative dP divided by the volumetric strain, dV over V. Here, dP is the increase in pressure. Now, that negative sign? It's absolutely crucial. It's there to mathematically account for the fact that as pressure goes up, volume goes down. If we algebraically rearrange all of this, we get negative V times dP over dV. Since volumetric strain, the change in volume divided by the original volume, is just a ratio and doesn't have an underlying unit, the unit for the bulk modulus stays exactly the same as the unit for pressure, newtons per square meter or pascals. And keep in mind, compressibility itself is simply the reciprocal of the bulk modulus. It's just 1 over K. So a higher K means lower compressibility. Now, what happens to our formula when we're compressing gases under different thermodynamic rules? Well, for an isothermal process, where the temperature stays perfectly constant following Boyle's law, the bulk modulus K is simply equal to the pressure P. Easy enough. But for an adiabatic process, where absolutely no heat is exchanged with the surroundings, K equals P times K, where K is the ratio of specific heats. Since K for a gas like air is roughly 1.4, which is obviously greater than 1, this mathematically proves that gases are inherently harder to compress in an adiabatic process than in an isothermal one. Let's actually run the numbers on a practical problem so you can see how this works step by step. Imagine a liquid's pressure increases from 60 to 100 newtons per square centimeter, and that causes its volume to decrease by 10%. Step 1, our increase in pressure, or dP, is 100 minus 60, giving us 40 newtons per square centimeter. Step 2, our volumetric strain is 10%, so that's 0.10. Step 3, we apply the formula we just learned. K equals 40 divided by 0.10, which gives us 400 newtons per square centimeter. When we convert that into standard engineering units, it equals exactly 4 megapascals. See? Step by step, the math flawlessly maps right onto the physical reality. Next up, Section 3. The science of surface tension, unlocking the secret of floating objects.
The big takeaway here is that surface tension acts kind of like a microscopic trampoline. Think of it as a stretched elastic membrane, or a skin covering the fluid. It's the property of the liquid's surface to exert a tensile force that is constantly trying to pull the liquid into a shape with the absolute minimum surface area possible.
But why does this actually happen? Well, we have to zoom in on the molecules. A molecule chilling safely deep inside the liquid is completely surrounded. It's attracted equally in every single direction by its neighbors, so all those forces balance out perfectly. However, a molecule at the very surface doesn't have any liquid molecules above it, just air. Because of that, it gets pulled much more strongly downward and sideways than upward. This unbalanced net downward force causes the surface to literally contract and pack tightly together, and that's what creates that incredible elastic skin we call surface tension.
All right, Section 4, Calculating Pressure and Forces, Mathematical Formulas for Droplets, Bubbles, and Jets.
Surface tension, which we represent with the Greek letter sigma, creates a pressure difference based on curvature, and the math changes depending on the shape. Let's compare them. For a solid, spherical liquid droplet, the internal pressure P equals 4 times sigma over the diameter d. But think about a hollow soap bubble. It actually has two surfaces, an inner one and an outer one, both touching the air. Because it has two surfaces, that tensile force gets doubled, so the formula becomes P equals 8 times sigma over d. Finally, a liquid jet, which is a long cylinder rather than a sphere, is governed by P equals 2 times sigma over d. When you look at these multipliers side by side, the 4, the 8, and the 2, it makes the underlying physics really easy to remember.
Let's put that droplet formula to work with a real academic example. What is the diameter of a water droplet if the surface tension is 0.075 newtons per meter and the internal pressure difference is 150 newtons per square meter? Okay, step 1, we grab our given variables. Step 2, we pull up our droplet formula. P equals 4 sigma over d. Step 3, we algebraically rearrange it to solve for d, which gives us d equals 4 sigma divided by p. Step 4, we just plug in the numbers. 4 times 0.075 divided by 150 gives us exactly 0.002 meters, or 2 millimeters. This exact calculation proves how a fine mist or a heavy fog is mathematically held together in tiny 2 millimeter spheres entirely by the sheer elastic power of surface tension. Pretty cool, right?
Let's get practical. Section 5, Real-World Engineering Applications, Bringing Theory into Practice.
So why do engineers actually care about all this? Well, when dealing with compressibility, even though we know water is almost incompressible, that tiny microscopic fraction of compression can be extremely dangerous. For example, imagine a massive municipal pipeline. If a huge valve is slammed shut abruptly, the massive kinetic energy of all that flowing water actually forces it to compress slightly. That creates a sudden, violent, high-pressure shockwave known as a water hammer, and it can literally burst solid steel pipes wide open. Compressibility also dictates the split-second response times in heavy hydraulic machinery, and it completely changes how water levels behave when we pump groundwater from deep aquifers. And surface tension? That invisible skin is doing heavy lifting everywhere. It causes capillarity, which allows water to totally defy gravity and climb upward through microscopic pores in the soil, something that directly affects the foundation stability of massive structures. Surface tension also determines how water beads up and rolls off of waterproofed building materials. Oh, and it's literally the guiding math used in agriculture and firefighting. Engineers use these exact equations to design nozzles that atomize water into the precise droplet sizes needed to perfectly cover crops or smother roaring flames.
Bringing it all together now. Section 6, Summary and Observations. Key takeaways from today's masterclass.
If you only remember one number today from the compressibility side of things, make it 2.2 gigapascals. This staggering number is the bulk modulus for water at room temperature. Because this value is so massively high, it proves beyond a shadow of a doubt that it requires extreme, enormous amounts of pressure to change water's volume even slightly. And that's exactly why for most everyday engineering problems, like designing a standard plumbing system or an open channel, we can safely simplify our math and just treat water as entirely incompressible.
I want to leave you with this powerful mental model. Fluids have stiffness and fluids have skin. Compressibility measures that stiffness, whether a fluid is highly yielding like air or unyielding like water. And surface tension? That's the skin, an invisible microscopic elastic membrane holding physical shapes together against the forces of the universe. I challenge you to look closely at your physical world today. Watch a spherical water droplet resting perfectly on a leaf, or see if you can gently balance a metal paperclip on a glass of water at home. When you do, you aren't just looking at water anymore. You are witnessing high-level physics and mathematics in beautiful, perfect action. But I'll leave you with this provocative thought. What happens to these precise equations when gravity is completely removed? How does a single droplet of water behave floating in the middle of the International Space Station? Think about that.
Thanks for exploring with this explainer, and keep observing the math in the world around you.